All right, so here we are at section 10.3, and what the first reaction we want to learn with radicals is the halogenation of alkanes. It's a very useful reaction because we normally think of alkanes as dead ends. If you remember back to when we were building our reaction maps, the methane was really dead end because it's the most stable of all the molecules we've been using. So it's nice to be able to go in the opposite direction. If we started with an alkane, how can we then build something useful out of it? So for this reaction, we're going to need to create something unstable to react with the methane because the methane itself is not reactive enough. So usually you see some kind of a radical initiator. In the past, you've noticed we use peroxide for anti-Markovnikov reactions that are radical. We're going to learn how that works, by the way. But usually it's a halogen or peroxide, and that's because they have bonds that can more easily be broken. And then we usually have some source of energy that helps to make that homolytic cleavage occur. So here, this is a symbol for photons, or light is h nu, E equals h nu, so it's sort of a universal symbol for photon. Or also heat. Sometimes you see a little triangle here, delta, for heat. So in any case, you see something like that as a reactant. So our first thing is we want to initiate the reaction by making this into radicals. So to do that, we're going to look at chlorine in this particular place, but it could also be bromine, is also very common. And with heat or light, in this case light, we're going to homolytically cleave that bond. So we're going to break it in half, and then we're going to have two chloride radicals as a result. So now that we have radicals, they're going to react with the alkane, which is more stable. So this is how we show the propagation step. Propagation means to take something you have and create more like it. So propagating your genes, for example, for if you reproduce. So in propagation, we take a radical and then we start reacting it with our starting material to make more radicals. We want to make our starting material into a radical. So to do that, I bring in this highly reactive radical, I react it with our methane. One of these bonds is going to break homolytically because the chloride radical is so reactive. And then we're going to make methyl radical, and we'll also make HCl. Okay, so in propagation, what's going on is we start with a radical and we make more radical. And then once we have that radical, then we can do several things with that. One is we could take that methyl radical and we can pair it with our chloride radical from, just floating around from the first step, like this. And these two can get together. And whenever you have two radicals and they collide with each other, they form a bond. And that's called termination because you've stopped making more radicals. Now, often you see this written CH3Cl. Okay, so there's our termination step. Another thing that can happen is this radical here can do something called a chain reaction. That is, it can continue to make more radicals. So to do that, I'm going to show you how we don't have to cut all of the CLs at the beginning. We just need a small amount of initiator to get this started, but we don't want to cut all of our Cl2s because they'll just come back together. So we just want a little bit just to get this started with methane. And then once we have methyl radical, that can actually behave in the reverse sense that it can cause the Cl2 to become radicals as well. So let's take a look at that. Methyl radical causes this bond to break, and then the reaction will go toward product, which is CH3Cl, but also we see chloride radical. And you can see how this is a chain reaction because now I've produced something that will start this all over again. So it'll just keep going. So in termination, sometimes there's multiple radicals floating around that can collide together to give you a mixture of products. So we see that methyl radical, chloride radical can get together, but also, there are other possibilities. Chloride radical can get together with chloride radical and make Cl2, or you could have CH3 radical get together with CH3 radical and make ethane. Just maybe a small amount of ethane around. So whenever you want to minimize that, you want to have just a little, you want to have excess chloride around compared to your methane, so you don't end up with too much methane seeing each other and colliding together. Otherwise you'll get ethane. But here's our major product, is right there. So multiple halogenations can occur if you have one equivalent of Cl2, so 1-to-1 mole ratio, you're likely to get one of these. But if you have a lot of chlorine, you can keep getting radicals out of it, and you can see multiple substitutions here till we get something called carbon tetrachloride. And in reality, you're going to have a mixture of all these because it's very difficult to control how many. But usually we try to do that with either excess, and so if you have excess, it'll be pushed, by Liz Chatelier's principle, be pushed all the way. Or you try to limit the amount of your reactants if you want mono or dichlorination, for example. So for this one, I'd like you to practice identifying, writing out first, your initiation. So you find out what are your initiators, and then use that to figure out your propagation step. And then show me your propagation. There's usually 2 propagation steps. So there's this one and this one. And then always look at what you're trying to form. In this example, it says for practice, just do the second step. So for practice, I want you to just take this reaction and show how you can apply this radical mechanism. And one more thing, when we do radical mechanism, we always write it out in steps. We always say initiation, and you show the reaction, propagation, and you show those reactions, and then termination, and you show those reactions. Okay? So try to follow that form and practice your arrow electron pushing.